Thank you. So apologies for the hiccup in the computing here. So I'm very glad to speak last because you all have introduced many things, many topics, many. So this is about mutual information, the callback library dimensions that we discussed earlier. I will talk about design, optimization, data assimilation a little bit. And this is work with Joachim Beck, my ex-postdoc, who's now at CAUS, Chao Yu Liu, who is my ex-PhD student, my current PhD student, Tao, and Aditya Guzman, who was until Monday at the University of Tokyo, working at the Earthquake Research Institute. So what I want to say is something about publications here. So it's very small, but I could squeeze in that the first paper with Joachim is in Siam UQ Journal. The second is with Xiao Yu in Siam UQ Journal as well. And what's funny is that the first paper is now the most downloaded paper in Siam UQ. And this, as of last week, suddenly became the second most downloaded paper. And I don't think it's because of quality. Let me be honest here. Why is it the case? To be clear, it's because the UK decided to invest in open access. So each paper that we have to that we can publish using grant money has to be open access. So I think very few papers in this journal are open access. It's quite pricey. So I think that's the reason, seriously, because this is interesting, but not not so hot, I imagine. The last paper is a paper that just accepted on emulation of high-resolution tsunami modeling over Cascadia, and I will talk about Cascadia in a second. So this is a bit too much on the slide, but it's the motivation, not introduction. The motivation mostly is about tsunami, and therefore how to make predictions that are accompanied with uncertainties. But this is time-consuming. If you want to do design of, let's say, networks of stations in order to do data assimilation optimally, which is the last part of my talk, it's very time-consuming. We can use surrogate models or emulators in statistics, we call them, to approximate computer models. So let me just give you a picture of what is emulation. Obviously, you've heard of it this week, emulation, surrogate modeling, but here we have model inputs that are themselves uncertain. And this is another paper, but that was on landslide-generated tsunamis. So if we have three distribution of the inputs, we propagate these uncertainties to the outputs, and we get a possible here tsunami wave generated by a landslide. This is one view of the propagation of uncertainties, thanks to the emulator, instead of using a simulator that's expensive to use, or computationally demanding. And here is an illustration. So in Google Earth, I can display here, I don't know if you can see, but there are three colors. So this is tsunami inundation for the city of Victoria, British Columbia, which is at risk. And this is the Parliament of British Columbia. Why am I showing the Parliament of British Columbia? Because we want to have an impact on policy, obviously. So if you tell the policymakers that your window here, I mean, your office is here and you're going to be affected, that's much more effective. Actually, this is based on evidence. In 1858, Great Stench in London. Why do we have a sewage system in London? Because of that only. Because it was smelling. It was impossible to work in Westminster, in the Parliament in London. The epidemics of the last few decades that killed tens of thousands of people, a few of them, not interesting to policymakers, but it smells in their office, it's interesting. So this is very nice. If I have internet, but I could show you, I could navigate this inundation, these hazard footprints to show you the impact it has on Cascadia. Well, since I'm talking about Cascadia, please look at this article in the New Yorker from 2015, which was awarded the Pulitzer Prize. Actually, it's a fantastic article. That's called the really big one. The big one is the typical, St. Andreas fault. The really big one is this one. We're talking about two-thirds or half of the hospitals and police stations destroyed. 15,000 deaths, and no electricity for 6 months across Washington State, Oregon. So this, yes. And the last tsunami was 26 January 1700. It's a paper by Kenji Satake from the University of Tokyo in Nature in 96. And these tsunamis occur every 400 or 500 years, 1700. So that's a fascinating article that vividly describes the risk. Anyway, so if we want to compute risk or to quantify uncertainties about the risk, about the hazard footprints locally, then we have to use emulators because it's unaffordable to compute all these possibilities. And you can see 3 bands here. It's a bit like a box plot. So the median, the 25% and the 75% percentiles here show the uncertainty about the possible next incoming tsunami. Not the full uncertainty, it's just a way of showing some skewness maybe. But it's much more fun to go on Google Earth and navigate these footprints. So Gaussian process is akin to polynomial chaos expansions and other techniques for surrogate modeling. I want to say that 2 weeks ago in Cambridge at the Newton Institute, we organized an entire week on surrogate modeling. You can see the videos online. We had a panel even, but that's not online. But on comparisons, on strength of these different techniques and strength and weaknesses, and it was fascinating to compare methods and also to highlight benefits. So here it's the typical plot of a Gaussian process that I borrowed from somewhere. I don't remember where actually. But this is just a simple function x sine x, assuming that this is the computer model that you are trying to approximate, but you actually know this function. This is just for illustration purposes. And you exercise the model at some inputs, where the red dots are. And in between those inputs, you're uncertain about the output that will be obtained by running the model at these inputs that are in between these 2 points, for example. Obviously, extrapolating is a dangerous game. So here you can see that you're outside this truth. And that's in 1D input, 1D output. Obviously, computer models is not 1D input, 1D output. So this paper, for example, this last paper, it's modeling of outputs that are functional. So we're doing entire time series of outputs. A bit, Mohammed was talking about outputs that are of this kind. A surrogate-based optimization, I will talk about it later. So the setup problem is that you have a function that's expensive to compute, and you want to maximize that function. It's an entire field of research. No, I mean, let's say not entire field, but it's very, a strong activity. Sorry. And so at the end of the talk also, I will talk about techniques that help us using surrogates that are of interest and their uncertainties. How we can maximize the information gained about F to optimize F. So you have a trade-off typically between exploration and exploitation, as we say. So again, it's popular. I'm not going to repeat all of this. That's you have nice properties. You can use the Gaussian distribution. So if you condition of the observations up to whatever you have in the samples, then you have a multivariate normal distribution. I want to say that it doesn't mean that the outputs are Gaussian. If you look at this, if you look at the input-output relationship, it doesn't mean that you're assuming Gaussianity everywhere. You're just assuming Gaussianity conditional on where you have exercised the model. You have a conditional distribution which is Gaussian, but that's it. Everything can be very irregular. It's very general. In some way, it's a stochastic process on functions. Typically, you have a mean function, a covariant structure. So the mean, well, let's say, you can use a simple linear mean. It's not so important. Actually, the action really takes place in the covariant structure. And this is a typical way of representing those covariant structures with a correlation here, correlation function. And you have families of correlation functions that are well suited for this work. So typically, Matern. The Matern covariance function that we've seen earlier also. This is a modified Bessel function. It looks scary, but what does it mean? It means that if you're far away, if you're close, in the input space, the axis of the inputs, right? Then that means that you are highly correlated in the outputs. So that means the closer you are in the inputs, the closer you are in the outputs, obviously. But to which extent depends on the length scale here. Those length scales say, well, in that direction, it's more or less the case that you are strongly correlated or not strongly correlated as in terms of decay in this direction. You have also smoothness here as a parameter. Obviously, this is in dimension d of the input space, and these are the length scales that are really governing this process of characterizing correlations. So typically, you do maximum likelihood, or you can do a fully Bayesian. You can carry out a fully Bayesian approach as well. I do both, but the MLE you can get those betas for the mean. Sorry. If you wish to, you can also impose a. I mean, you can use a zero mean function. It's okay. Sometimes it's fine. Sigma, the MLE of these, this C vector is made of these length scales. So this is standard stuff. I'm not going to dwell on this, but what we have in the end, we have these predictions of the mean and the uncertainty about our prediction sigma hat, both. The challenge in red is how to fit a GPE. So the problem is that it scales with n cube. It's the fact that you're using here. If you look at the, you have a log determinant, you have inverse here, and typically U shall SK. U shall SK. I mean, so that's really a problem. That's where Gaussian process suffer. So I mean, I'm suggesting today two solutions. I'm not the only one suggesting solutions. There are very smart people working on this. Dimension reduction or smaller design, right? If you either you reduce dimensionality of the problem or you sample in a way that's more efficient. So I was not going to talk about dimension reduction, but since Loïc talked about it and many others, so how do I switch from a I don't understand.